of explosive charge, actually. Most wells today are completed with the production casing cemented in place and perforated to allow reservoir fluids to enter the wellbore. Okay, and the current perforation techniques use shape charts. I will mention these as well to produce penetrating jets which perforate through the casing and the cement sheet. Flow-through perforations affects the productivity of a well primarily by changing the local flow geometry near wellbore area. Okay, so let's talk a little bit about the history of the perforating in oil industry. First of all, the foundation of the invention of nitroglycerin is nearly 1860s. Okay, and before 1932, the mechanical cutter invented. Up to date, but the mechanical cutters, the performance of these were very, very low. After that, in 1932, the bullet guns started to use as perforating materials. These bullet guns were the first commercial perforating devices. In this system, a hardened steel bullet was fired from a shot barrel gun powered by a gas-producing explosive. Okay, kind of hydraulic mechanism. There is a gas-producing explosive in the end of that, and this short barrel gun powdered in it, and explosion happened. So these guns first saw commercial use in early 1930s, as I said, 1932. It applied, of course, very limited penetration to your reservoir. The wall thickness and hardness of the casing and the hardness of the formation limits this bullet perforating actually. However, bullet guns are still used in some applications. Still in today, it can be used when, for example, when your reservoir is loose. If it is very loose, so bullets can be a solution still, okay, because it's very limited and can be a good solution for loose formations. So, as I said, gullets still used in some applications, actually in soft formations for deep penetration or brittle formations in which the shattening produced by the bullet can help break down the formation around the perforation. Okay, so the advantage, still we are using this because the advantage, we can say, it enables a high permeability connection to the immediate reservoir if you have a loose formation. It is very controlled, hole size and shape as well. You know the shape, you know, it's a bullet already. You know the shape, what it can, what type of penetration you can get, you know it, okay? From one charge to another, it's not changing too much, so you know the penetration length, the depth, the area, you know most of the results, okay? So this advantage, actually shallow penetration, okay, not it cannot reach along 50, 60 centimeters, 30, 40 centimeters, whatever. Very few penetration, like 7, 8 centimeters, maybe 5, 6 centimeters, like this, okay? So another thing is ineffectiveness in hard formations and high alloy or heavy pipe problems, okay? The weight can be a problem. And it's ineffective in hard formations. So just for loose formations, you use this. Another disadvantage: leaving a solid mass of steel in the perforation tunnel. So there is a debris in the perforation tunnel remains. So this debris can create an extra skin factor. Okay, so if it cannot be cleaned by using the special techniques, so this debris will create extra skin. And this will be harmful for your production and productivity index, okay? And another disadvantage is low density perforating, we can say, okay? So shot density is very low, so it will directly affect your production in the end because your perforation tunnel will be very limited. So, following the usage of bullets, shape charts invented and start to be used commercially starting from 1946. Actually, firstly, during 1930, 1940, beginning of 1940s, in World War II, actually, these shape charts progressed in the military area, first of all. Okay, the bazooka, as you know, the bazooka with its armor-piercing charts was one of the first large-scale used in technology pioneered in this area, actually. It's developed by a guy called Henry Mohab, and this technology directly taken to oil industry and started to use in oil industry in perforation as perforation, one of the perforation techniques, starting from 1946 actually. Still it's widely used, shape charts widely used in the industry. And these, of course, in the same years, it started to be used with wireline perforation. Okay, as wireline, there is a wireline cable. They were putting this in the end section of this wireline cable and pulling inside the hole. And when it comes to the certain depth that they want to perforate, directly the explosives they are making the explosives, putting the explosives and making the procedure like this. Actually, these shape charts, or another name is jet perforator, uses a small amount of high explosive and carefully shaped case and liner to create a focused pressure punch that is highly effective in piercing steel, okay, cement, and also rock. So it has to be effective in steel, in cement, and in rock. So there must be herein material science is very crucial to enable this. Now, of course, with the developed technology, new materials involved to the game, and they are using these explosives and materials which are very effective in, of course, steel, cement, and rock. So the jet is performed through a highly critical but usually reliable sequence of events. Actually, I will mention these later on. The entire sequence of the explosive event must be carried out in high order, and you have to be very careful when you are applying these procedures actually. So it's very crucial, step by step, it has to be applied. So after that, another method called abrasive jetting started to apply from 1958. Actually, started to be applied. In these types, this abrasive jetting method, it uses a high volume flow of abrasive leaden fluid to erode through the target pipe or cut it off when the nozzle or tubing streak is rotated. Okay, a little bit technical, I know, but when the nozzle or a tubing string, there's a tubing string or nozzle, when it is rotating, it's making its firing by applying a high volume of flow, okay, jet flow we call. So abrasive perforating methods are slower. It requires a rig, of course, and contains several wear points in the treating equipment. So it has a kind of operational disadvantage. It's applying in some certain areas, but not too much. It's not a selected method in the industry, actually. So starting from 1978, another method called tubing conveyed perforation started to be used. What is the difference compared with the wireline perforating? When you are making wireline perforating, you are using a wireline cable. There is a connection between surface and your guns, okay? And with tubing conveyed perforation, we call it TCP. You are using a tubing string for this one, and there is no connection with the surface. So these works clockwise. Okay, so you are timing it according to the timing. When you reach to your depth, you are calculating when it will reach to the certain depth that you are planning to perforate. When it reaches to that certain depth, so it fires, okay, in a certain time. This is mostly used up to date and still one of the favorite methods. Of course, there are now some developing technologies. There are some connections. What happens, for example, Schlumberger had some repeaters. They were using some repeaters, putting some repeaters and establish a connection between the downhole and surface, remote connection. So without needing the timing, clockwise usage, because it increases the operational error percentage a lot. So repeaters can be a way to use this one. Still a developing technology, but Schlumberger is using, as far as I know now. Okay, so as we said, tubing conveyed perforation also one of the alternative methods, actually favorite methods that use with wireline perforations. Okay. Also, you can use this one with coil tubing as well. So, your perforation can be used with coil tubing as well. Okay, for wireline perforating key materials I'm talking about. Okay, so let's talk about the shape charge history. The cavity effects, the explosive cavity effects. So you can see the three types in here. One of them is line cavity effect. Okay, there is a metallic liner in here, the explosive, the metallic liner. There is a steel target. So these are experimentally, of course, achieved results. So there's a steel target, you have your metallic liner, and it gives, as a result of that, the results of the explosion, it gives you a line cavity effect. Okay. So there is another metal liner effect, it's unlined cavity effect. So it gives you a shape like this, as you can see in the second figure. So these two are the main used techniques actually. The first one is mostly used because most of the reservoirs are tight compared with the loose gravel pack, that type of reservoirs. Okay, so in terms of penetration area, this tunnel wave is the best option actually. So this cavity effect is experimentally researched by Franz van Bader in starting with with very old timing, 1792, and then it's rediscovered by Charles Munro in 1888, and it's known as Munro effect in USA and Newman effect in Germany. So both guys at the same timing they discovered this actually. Metal liner effect. This metal liner effect early worked in Germany, United Kingdom, Russia, Italy, and Japan. So 1911. The main reason of making these experiments actually military reasons actually. Okay, not oil industry, military reasons. But later on, it adapted to oil industry directly because they saw that it's very effectively can be used to create a penetration area with reservoirs. Okay, so after this cavity effect and metal liner effect, using this type of things, they invented, actually Schlumberger invented this. They invented powdered lines. So these powdered liners, the usage of powdered materials, they realized that it gives more effective penetration area and more effective productivity compared with the others. So they selected to use these powdered liners, and it started to be used starting from 1960s.
Please, can you mute your voice?
Right. Still I'm waiting.
Imtiaz, can you mute please? Okay, teacher, you can start.
All right. So as we said, powdered liners start to be used like this. Okay. So this is, as you can see, this is one of the mechanisms that used in early times. You know, this is used for creating a metal liner effect. So as an example, I put this one. Now I will continue with the powdered ones. Okay, this shape charge is the most common way to use in oil industry up to date. Okay, so how this works? Actually, the materials are quite simple. It has a case. Okay, it is a primer explosive. You are putting your primer explosive. It has a detonating port, of course. This is just one explosive. Okay, so you have with along the depth. Okay, you have certain explosives which located in different conditions with different angles. Okay, you are calculating these angles, the conditions of each charge. And you are choosing the best design actually, which you can have the maximum productivity. So there are programs, there are softwares which are doing this. Schlumberger has one of the strongest ones. According to that, you are making a perforation design. So herein there is a detonating cord in the center. Okay, this is the center. Think about that. This is the center of your line. Okay, say wireline, for example. There's a wireline, and this detonating cord directly connects to your wireline. When you push to your button, this directly what happens? Activated with the detonating cord. And near of detonating cord, you have a primary explosive. Okay, you have a primary explosive in here. This is your case, as you can see, your case here. Your primary explosive is here. So you have a conical liner, this liner, okay? Between this conical liner and the case, they are putting the main explosive here, okay? This is the main explosive charge, okay? It's a powdered material, and it is the main explosive. You know, by using this primary explosive, all the explosive explode. Okay, in milliseconds, all the explosives start to explode. Okay, so and after the explosion, what happens? All the power, according to this shape, okay, because this shape designed because of that. According to this shape, all the power and energy, okay, combines in this part. Okay, in the center part, and then when the explosion in the next milliseconds, when the explosion happened, this directly sends all the energy as a line, okay, as a line through to your wellbore, your casing, and then your reservoir, okay, as a line. After that, it creates a perforation tunnel, okay, as you can see here it can be seen. Okay, so let's repeat it. This is wireline cord. You detonated your primary explosive explode, and then all your explosive exploded. It combined all the energy in this part, and explosion continued as a line. It passes your valve or your casing and your reservoir. Okay, so this is the main mechanism, how it works. So when you look at the lower part in the left section, you can see different types of cases and liners as well. So so when you check all in different shape and different sizes. So according to the usage of these change, there are some parameters which affects the usage of these. For example, if you are using a loose formation, you will use it in a loose formation in an open hole, for example. you have to select these two. Okay, according to the, of course, how much energy you want to create, and what is the stability of your valve. These need to be checked a lot. Okay, how many explosives you want to use, how many charges you want to use. These also need to be checked. And for example, depending on your, for example, your depth is nearly 2,500 meters or 3,000 meters, and you drill with, I had some cases like that. You drill with, you have a 4.5 tubing, and you are doing your operation from this 4.5 inch tubing. So in this case, you have to use a very small explosives. Huh? According to the situation, of course, if you are using 7 or 9 inch liner you have, for example, so it will change that. So let's pass this part. Okay, these explosives. Of course, this high energy, there's a chemical reaction happens in there. Okay, if there is no reaction, you cannot make an explosion. So explosion enabled with a chemical reaction in here, and of course, most of the chemical reactions release gases. So these also release gases. Okay, so this characterized by the speed of reaction, the pressure generated, strength of the pressure generated, the sensitivity, and in the primary high we can say detonators. According to the detonators, it can be classified. In the secondary high, of course, detonators, boosters, detonating cord, and shape charts can be a classification base as well. Okay, but the thing is, what I was doing when I was working with these, actually the most important characterization way is actually the speed of reaction and how much pressure it generates, because the pressure gives a very good idea regarding on the properties of your gas and its interaction with your reservoir array. Actually, I will mention these as well. So the oil industry has using a kind of explosives as mentioned in here. For example, RDX is cyclotrimethylentrinitramin. Okay, this is mostly used. RDX are mostly used. For example, the speed of this says 8,750 meters per second. It has a potential to go around 8,750 meters per second. Okay, when it explodes, the speed is like this. So HMX, also another one we were using as well, very commonly, is octogen, is 9,100 meters per second. HNS is hexanitrostilben. This is 7,000 meters per second. I am talking about, of course, in air condition. I am not talking about the formation. Here, these speeds are in the air. Okay. When it comes to, there are some, of course, materials which prevents. Of course, it will change directly. I will mention these as well later on. There are HNS, as I told, PET-N, TATB, Nona, Takot, PYX, and SX2. SX2 as well, also one of the common ones. Lead acid and silver acid, two different types. Actually, flammable solids, propellants, and low explosives are the units that used as perforators in the industry. So in this figure, you are seeing also the temperature rating of these explosive systems as degree Fahrenheit. So the most high temperature is belong to SX2, as you can see, and second one HNS, HMX, and RDX are classified in respectively. Yeah? Okay. Okay, so I actually gave these names because when you involve the industry, you could get familiar with these names, and it will be beneficial for you when you are making a selection. It will be beneficial for you in terms of reaching, in terms of making a research regarding on the properties of these different chemicals, explosives. Okay. Okay, how a shape chart for I already discussed about this one. It's how jet tip how jet tip formed and how it makes a tail particle sent as a line. Okay. For example, let's talk a little bit about timing. Okay, to make visualization physically in our minds. So initiation of jet happens in 0 to 15 microseconds. Okay, 0 to 15 microseconds. It's very fast happening. Okay? So initial response of the wellbore fluid, 3 to 15 microseconds. Sorry, milliseconds. 3 to 15 milliseconds. Perforation damage removal is creation of cavity. Actually, first of all, creation of cavity in rock also 15 to 250 microseconds before that. And then initial response of wellbore fluid happens 3 to 15 milliseconds. Perforation damage removal 1 to 100 milliseconds, and response of reservoir more than 50 milliseconds it happens, but not even a second. Okay, all happens not even the time is taking not even a second, and just before a second you get your response from your reservoir. Okay, so it's a very fast process. Okay, yeah, there's a visualization. I hope that you all can see this clearly in your screens. So according to time, and this is the maximum time herein is 1.4 times 10 up to 2 microseconds. So see how it happens. You can see clearly it gives you a good, I think, visualization. This is the same thing that we already discussed. Okay, herein how many centimeters it reach. It's this is a model actually. It's given as a model. It reaches the form. I don't know formation type actually, but it reaches up to 20 centimeters. Up to 20 centimeters in a very fast timing. Okay. So type of shape charts, of course, we can discuss this one. So for deep penetrating, pressed powdered materials and long cones can be used. Okay, this applies a deep penetrating, more deep penetration if you are aiming to get. So you have to use deep penetrating like this. Not for shales and unconventionals, of course, this hydraulic fracturing is totally a different thing. But for tight reservoirs, tighter reservoirs, you can satisfy this deep penetration, okay, by using these pressed powder metals and long cones. So if you want to create a big hole, so you can use solid liner and parabolic liners. So for good hole also you can select. You have some selected materials. I will not mention in here. Reactive liners, and for low debris, zinc or treated steels can be used. This low debris is very important. So most of the cases, when you created your perforation tunnel, there is a debris stays in your perforation tunnel, and it definitely prevents the productivity ratio. So if your if you have a debris like this and it prevents your flow, so your operation becomes unsuccessful. Okay, there are hundreds of operations worldwide. You can see like this when you check the history. Hundreds of operations like this, because they are just doing, we are making perforation. Okay, let's perform it, do it. What you are doing, you made any model, you analyzed that, you described what type of charts you will use according to your formation, your casing. Do you have any idea regarding on your wellbore structure? Because it's another thing. These are very important parameters. And in the end, if you want to get low debris, you can use zinc or treated steel materials in it. It will create low debris. Okay, the types of guns also, capsule type of guns. These can be exposed and wireline type. Carrier type of guns is protected one, or any conveyor can get it with coil tubing as well. The special guns, pivot guns, side mounted guns, oriented exact, it says this Shlamari product actually, and pump over type of guns. So I just put this one to give you an idea regarding on the shape and how it happens. For example, when you check the first figure, as you can see here, there is a charge and the direction of the charge. Okay, check the direction of the charge. And when you check the direction of this charge and compare it with the second one, there is nearly, as far as I can see, nearly 45 degree difference, right? 45 degree difference. And one by one, again, 45 degree, 45 degree, 45 degree, you see? So all the structure with the depth is changing like this. So this can be 45 degree, maybe 30 degree, maybe 60 degree, according to the program, the model. It will give you what type of penetration you can get, the better efficiency actually. Okay. So because of that, they are selecting these angles. Okay. So as I mentioned, there is an electrical detonator. If you are using a wireline based structure, wireline based materials, so there's an electrical detonator. There is a wire leg in here, rubber plugs, of course. It comes directly through to the RDX. For example, RDX is used in here. It detonates directly by using the wires. Okay. So another one is secure initiator, the EFI. There's a wireline input as well, can be used in here. There are electronics, and it directly electronically explode. Okay, these are wireline perforating types. So for the tubing conveyed perforation, actually there are two ways. Actually 3 ways with the repeater also you can do, but the 2 main things. There's a pressure transducer in here, there's a battery in here, controller circuits, initiator circuits, and EFI detonator as well in here. Okay, so we call this E5. Okay, compared with the prices, these are much more expensive, of course. And if you are a mid-range of company which cares about your consumption, your costs, most of the companies are not going with this one. But if you are a big company, so you don't care, you say that I would like to minimize any error operationally, so you are going directly to use E-fire system. The another one is the mechanical fire height. It uses a percussion detonator actually. Okay. So according to this, it applies direct, totally mechanical structure it has. This is cheaper compared with the other ones. As I told, now the most expensive one is using with repeaters directly connected to surface. Okay. Okay, this is this TCP DST string we can see here. Okay, let's give a little bit about this. This is the TCPs are used with the DST strings. Okay, what are DST string? DST string is a material that carries a gauge carrier. So you have your pressure values. Okay, you have your pressure values. Retrievable packer to isolate the perforation with your gauge. Okay, because if you perforate it, your gas, it can be harmful for your gas, so there is a packer isolation needed. There is a up and guns are in the lower. Actually, you get your data. Okay, you can flow before your perforations, and after your perforation, you continuously continue to your flow. So it's very very advantageous actually. Okay. Other types of deployment we said, apart from wireline and tubing, slick line can be used as well. Coil tubing, as I mentioned, coil tubing can be used. Completion types also enable, and tractor. But we can say these tractors mostly used in horizontal wells. Okay, it's better for horizontal wells because using a DST string in horizontal wells, it's not possible. Your DST string stays in the vertical section of your horizontal well and reads your pressure temperature data from the vertical section. And according to that, you calculate the results of your pressure and temperature recalculated according to the depth of your horizontal section. Okay, so because of that, it's very hard to use DST string. Wireline, it can be used. There are some materials to use in wireline. These tractors also can be used in wireline as well. But mostly tractors used with slick line, coil tubing, and completion materials. Okay, so in subsea environment also it's very useful materials. So. Okay, so let me open this one to make it. Okay, for example, so in the part, I would like to put an example in here regarding on the formations that I studied in Northern Europe. Actually, the permeability anisotropy is one of the main mechanisms. Okay, permeability anisotropy is very crucial. When you are making your perforations, you have to take care of this. Okay. The shale laminations, the wellbore damage, the natural fractures, carbonates, sandstones, and for example, the structures combines, the structures forms these carbonates. Okay, stylolites, for example, the alignment of grains and deposition in sandstones. These type of things are very crucial. The selection of your guns, and the selection of the directions of your guns. Okay. So productivity of perforated completions in fractured reservoirs requires a good hydraulic communication between the perforations and the fracture network. Okay, so you have to know the type of your fraction and the length. I cannot say length actually. The directions of your fractions. Okay, so according to this, you have to select the right design for your perforation materials. Okay, it can be 45 degrees, it can be 135 degrees, as you can see here. Okay, from one to another. So this is the actually design, like your test design, like your analysis, other analysis. This is also another test design and analysis perforation design. Okay, so parameters that maximize the chance of intersection a fracture are the penetration length, your penetration length, how high your penetration length is. The chance of making a cross section with a fracture is bigger. Okay, so because of that, it increases directly your penetration area. Okay, if you reach a fracture, your penetration area increase. The phase angle is crucial, and the shot density, of course. It has limited effect, but it has effect. The shot density, also one of the crucial factors that affect your productivity. For example, in this location, sorry, there's a question. Is geomechanics like principal stresses has to be considered when determining phase angle? Exactly, very good question. Definitely, we have to use these values. We are already using these values. For example, UCS value. Okay, what is the compaction, what is the strength of your rock, what's the strength of your rock. These mathematically as an input value, you have to put it to your software. I will mention later on. Exactly, this is very crucial, very crucial, very good question. Okay, I will mention the details of this one mathematically. It's coming. Okay, so for example, the popular gun configuration in northern Iraq was 60-degree phasing with 5 shot per foot. Okay, in one foot if you use 5 shots with 60-degree, okay, you get your highest penetration according to standard API tests. You get your highest penetration in the region. Okay. Okay, so let me continue. Okay, the penetration. Let's go to the penetration. For example, there's an example in here. This is one visualization that has been done by myself in 2013. Here, for example, what happens? The aim is you created your perforation tunnel. Okay. According to your formation, the specification of formation, you can if you are in overbalance condition, you can create extra fractures, little fractures in here, and one of these fractures, or most of them, can have a connection with your fractures. Okay, natural fractures in here. So this is very good thing if we can achieve this one. Okay, I will mention this one. So let's go for penetration. Okay, what happens? Penetration basics. Okay, so we said jet tip forms the first, goes fastest. The first part, we said that it combines all the energy in one point and goes as a line, right? As a jet line. Okay, so in the jet tips forms first, goes fastest. Okay, this particle goes fastest and it creates debris as well. Okay, so this is 7 kilometers per second, the speed. Okay, and then in the jet tail forms later, goes slowest one. This is 1 to 2 kilometers per second. Okay, there is another section in here following the first part. It happens like this. Okay, with this shape, it happens like this, and this is the second form. This is the slowest one. Okay, and when you compare the velocity and with the position, with the length, we say, you get something like this. The velocity gradient along jet, you can get something like this. The most linear part of this graph, you can get the velocity as the velocity gradient. Okay. So let's visualize a little bit more. Jets gets longer over time in air. In target jet tip is consumed. Okay, you can see what happens. This is real experiment actually. Okay, this is the first part in T1. This is the fastest part. We said 7 kilometers per second. Okay, it's going like this, and it's creating a debris as well. It goes as much as it can go. Okay, and then later on, the second slowest part go as sweeping effect. Okay, it making sweeping effect and going through to this. But the maximum length that it can reach is creating with the fastest material, fastest particles. Okay, the earliest times and fastest particles. Okay, all right. So hypervelocity penetration, we call it hypervelocity penetration. The high impact velocity results with high impact pressure. Impact pressure and impact velocity squared is the calculation formula. Actually, it's the pressure is a function of the rho jet and rho total, and the velocity square of your velocity. Okay, so your penetration velocity is described in here. Your PT and PZ is described as in the formulas, and your penetration can be calculated like this. If the impact velocity and the jet density is high enough, then impact pressure is much more than the target material strength. Okay, target material will flow like a fluid, not melting, but it will flow like a fluid. Okay, because of this very high pressure, effect of very high pressure. So the perforation tunnel is created like this. Okay, the penetration depth is proportional to the jet length. Okay, it does not depend on velocity, but it's proportional to the jet length, we can say. So depth of penetration formula is given like this: the length, and it's a function of the length, the rho j and rho total. Okay. So okay, so kinetic energy. Okay, let me open all of this and combine all of this. So we consider there are two rods now. Okay, we have two rods with equal energy and diameter. These two rods has equal energy and diameter, and the difference between the velocity and mass in terms of length. So the velocity and mass, long for low velocity, and you get low impact pressure. Okay, short for high velocity, and you get high impact pressure. Okay, so rod A, long, low velocity, low impact pressure, will not create sufficient pressure. Thus, rod B will be hard target optimized. Okay, and rod A and B both create sufficient pressures to penetrate soft target. However, rod A is longer, so rod A is soft target optimized. Okay, we can say your model. When you put your input pressures, your model give the results like this. So when you see the depth of penetration with the ballistic indicator function, for example, the plots for stroke rock charge, you can see for conventional charge, it has to be like this. So weak rock charge, as you can see, your depth of penetration combined is shows higher compared with the other two. Okay. So these are a little bit technical. I was just giving you to give some idea regarding on that. Okay. So perforation tunnel geometry. So you have in your casing part, you have a diameter of D. Okay. Following your perforation tunnel created, you have if you have a diameter of D in here, so the perforation tunnel diameter will be 2 to 4 diameter of D. Okay, up to 4 you can reach, not more than 4. So you have a certain permeability and reservoir pressure as mentioned in here. So you have relative impact pressure as well. Okay. So as you can see, your cement as well as its cemented material. So this tunnel, as I mentioned, generated in 100 to 300 microseconds. Okay. So there is something in here. What is this? There is a KC here. We call it crush zone. So your debris material are here. So after you created your tunnel, you still have some skin. Still have some skin in your perforation tunnel at this time. Okay. So you have to get rid of. You have to get rid of this skin by flowing. Okay. You are with the pressure difference and flowing. By time you can get rid of this. Some of them, not all of them, but you have to apply something which is very effective. You have to adapt in here. So there are some ways of applying this. So we will mention these as well now. Okay. So for the prediction of this penetration, there are some experiments done in the laboratories. Actually, most of them firstly done in the laboratories. According to the behavior, you can see the materials as well in here. What type of materials they are using? With concrete, they are using with rock materials as well used in here, but mostly they are using it with concrete first of all. By using certain gun samples, examples, and they are making predictions. For example, sorry. Okay, for example, first of all, you have to test your rocks. Okay, what type of rocks you need to perform. So what happens? For example, there is a company, they want to make an optimization for their perforation. Okay, first of all, the rock samples belong to that well that can be taken and sent to laboratory of this perforation laboratories. Okay, to make these tests. They can get some samples, and the rock characteristics need to be described. It's weak to strong rock. What type of rocks these are? Okay, so these need to be described first of all. The main parameters for rocks which describe this called UCS. This the unit of this is PSI. Okay, so according to this UCS value, you can characterize. It's very important factor to characterize the type of your rock. Okay, so you take your rock sample in situ, you make your analysis and say UCS value is this one, and you can send it to you can put it to your model directly with the porosity, of course. The second parameter is porosity. UCS value and porosity are two main parameters to describe the characteristics of your rock and put it to your model as input value. So geomechanics is important. It's very important in terms of describing this UCS because it shows you the strength of your rock through to the penetration, through to the perforation direct. Okay, so it's a very crucial parameter. And for example, if your UCS, see, for example, there is a Castlegate rock type in here. You say 1000 UCS, 1000 PSI UCS, and there is a nugget in here, 16,000 UCS. When you compare these two, okay, one of them you maybe create 5 to 6 centimeter penetration length, the other one 25 centimeter penetration length. Okay, so it's very crucial parameter to describe. And what happens, what we are doing actually, for example, you have a rock type like nugget. Okay, so 5-6 centimeter penetration length. How I increase this length? Okay, how I optimize and how I increase this length? Okay, so I am searching the ways of this actually. So largest ever range of stresses 1 to 20,000 psi. Okay, UCS values maximum 20,000 psi. When I was working in Iraq, we were reaching up to 5 to 6,000 UCS values actually. So it was not a harmful situation, but there are cases, especially in US, Canada, there are some cases that the rock samples, that the rock UCS reached to 20,000 psi. Okay. So according to these UCS, different families of charts has to be used. You cannot say I am doing perforation without knowing anything. But today, most of the companies are applying. I know it from some locations that I work. Without knowing the details and parameters, they are doing. We make the perforation. Okay, done. What happened in your perforation? What's your penetration length? What's your productivity? How it increased? How it affected? Okay. Okay. So because of that, what happens? You are selecting the rock type. You are seeing that your in situ samples you took. You said that my UCS value is like this. So they are selecting the closest type of rock. Maybe it can be an outcrop or something like that, which is very close to that UCS value, and making some experiments, okay, by using the capsule charts, okay. All right. So the details regarding on these studies can be seen with the SPE 127920. Okay. You can check this SPE material, and if you have any questions, you can ask me directly. Right? So let's compare the most crucial types of reservoir rocks, sandstones and carbonates. Okay, let's compare this one, the results of this. This depth of penetration with the ballistic indicator function, we say PSI. Okay, UCS value we say. Okay, so when you see the sandstone depth of penetration is a little bit more, the average I am talking, a little bit more compared with the carbonate ones, right? A little bit more. So, for example, then the Austin chalk type of rock, the UCS is around 3000 psi. For Indiana limestone, 7600. Carthage marble, 20,000 psi UCS it can get. Okay. Of course, it directly when it increased, your penetration depth is decreasing as well, right? So reverse proportion. Okay. The system effects. As I mentioned from the beginning, the system effects, the phasing, the shot density, gun clearance, interference, gun scallop, they said, okay, these are the parameters that affect the system. So all need to be calculated and need to be checked well, okay? Previous start the operation, all need to be checked and all need to be calculated. Your casing size, the thickness of your casing, grade of your casing. These are all input values to your system, okay, to your model. And well fluids, of course, mud weight, okay. These are very important parameters need to be put as an input. So, of course, another thing is here, as you can see, what is the location of your charge when you compare the whole well section, okay? You see the diameter, maybe it has gone to the left side, okay? Your tubing gone to the left side. So what it will be, your penetration will be totally different in this case, okay? So according to this, you have to make some case analysis. You have to, for example, if it is centralized, what type of penetration length and what type of productivity you will get. If it doesn't have any, you say in somewhere in the left side, for example, what type of penetration, okay? Or it can be positioned. Why? It can be positioned. Why? Because in some parts of your reservoir, for example, if you have classified according to situation, according to the case, actually. This is the main parameters of the system effect. So there's another study, SPE paper. Here it uses this is also Schellenberger study. It uses these perforation analysis actually. As you can see here, this is the perforation analysis result. It's the result part. It gives you the result according to the certain pressure and temperature value in your wellbore and your absolute open flow values as well. Okay. So the maximum penetration lengths can be calculated by using these inputs and this model actually. So what it makes in here, for example, in this study, 2 rock tests of the NIV section has been used with 3 rock stress combinations, okay? And the ballistic indicator function is too much technical. It's FBI we called. This is also another function parameter we are using. According to these, the charge is characterized and the best charge selected. Okay, it gives you, the program gives you the first 3 charges, favorite charges for the system that can be used. Okay, so it characterizes your charges, and according to these charts, it creates a new penetration model and productivity. Okay, it gives you the penetration depth, and with this penetration depth, what kind of productivity index you can get. Okay, all this calculated, and according to this, it gives you all the results, and the results can be seen. Some part of the results can be seen here with the type of charts that need to be used. Okay. Yeah, direct link to rock. Okay. So here, two different cases. This is okay. Your perforation tunnel is created. Okay. So as you can see here, this is a balanced perforation example. Okay. And this is underbalanced perforating example. What is underbalanced perforating? What underbalanced perforating is? For example, what is the main difference in here? In balanced perforating, you can see just the line, right? Just it created a line, but you are not in underbalance. If you are not in underbalance condition, which means that your reservoir pressure is low than your wellbore pressure. Your wellbore pressure is higher. So what happens? It continues to push. Okay, you created your tunnel, but the pressure of your well continues to push your reservoir. Okay, I'm talking about milliseconds. Okay, in milliseconds. So it continues to push your reservoir. So what happens? The debris that created here, you can see the debris line here, right? If you look at carefully, you can see the debris lines. Okay, actually the tunnel, not like this, tunnel like this. You see the debris lines in here, right? But it's still in there, so it prevents the flow. But if you are making it under balance conditions, so what happens? It creates direct the tunnel like this by taking the debris, because the under balance conditions, your reservoir pressure is 3000 psr higher than your wellbore pressure. So directly when it's flowing, it also what happens? It sucks the debris through to your wellbore and gets to the upper part. Okay, gets to the upper part directly. So it's very crucial when you are making your design, you will be in overbalance condition or underbalance condition. Okay. So in the end, crash zone affects by production and injection, fill, fines, or debris affects injection, of course, according to the situation of your well. Okay. Okay. So this is perforation tunnels. This is normal perforation. You can see the debris in here. There is a debris in here, stays in there, still in there. So let's make a kind of view in micro scale. So this is the crash zone, right? Crash zone. See, this is the crash zone. Means that it's exposed. It exposed. This part is exposed to the explosion. Okay, so what happened? It directly isolates. You can see the micro scale. The pores that very limited. The pores are very limited compared with this virgin rock part, right? So it's isolating my reservoir, still isolating my reservoir to connect with my wellbore. Okay, so I have to get rid of this part directly. You can see the same section in another view. Okay, see, there is no pore in here to satisfy a kind of flow compared with the virgin rock. Okay, so because of that, I have to get rid of this basically. Okay, so crash zone affects both production and injection. Debris within the perforation tunnel affects injection as well. So you can see the SPE 31083 for the details and how you can get rid of from this debris part. Okay. So okay, you are in the static underbalance. Your wellbore pressure is lower than your reservoir pressure. So some part of your debris can be taken. Okay, this is a good way also without doing anything. This is a good way as well. But the most effective way compared with all of these three is dynamic underbalance. What dynamic underbalance means? When you are making your perforation, when you are detonating your explosives, at the same time you have to be in underbalance condition. Okay, you have to be in underbalance condition. Then your detonator explodes. It created your tunnel, and directly it sucks. It sucks with underbalance effect. Created your tunnel, and then it sucks your debris directly through to your valve wall and upper parts. Okay, so directly as a part of your perforation operation, directly you get a clean perforation tunnel without debris. How it happens, we will discuss. By using the UCS values of the real rock samples, they are creating the concrete with the same UCS value. Okay, and they are applying the experiments by using these concrete blocks. Okay, this is the chamber of using these experiments effectively. There are certain ways. This is I think 15 to 20 different chambers like this in the same location, and they are making these experiments. So, as I said, block of rock in stress frame, according to the stress description of the rock, they are creating the same thing for the concrete and applying the experiment. They are enabled to shut in underbalance as well, okay, for creating underbalance conditions. So because of that, static underbalance can be applied. So measure flow from each perforation using straddle assembly. Okay. They analyze the data of this. So there is one case study with Schlumberger with BP. If you're interested, you can check this paper for it as well. Okay. SPE 28554. Okay. All right. So for the static underbalance condition, there are two cases. One of them is 500 psi underbalance. The second one is 200 psi underbalance. So in the first one, the PI is 0.07. In the second one, the PI is 0.2. Okay. So what happened? They flowed the well, they killed the well, and they flowed the well again. Okay. In these two, compared with these two, they flowed the well, they kill the well, and then flow the well again. Okay, so let's check the results. After killing the well, your productivity, your perforations, according to your perforations, okay, they give. After kill, it gives 13.5. Before the kill, it was giving 37.5. After kill, it was giving 47.5 in this 2000 psi underbalance. Before killing, it was giving 55. So killing, what can I say? Killing is not a good thing, even with better kill pills. Okay, it's not a good thing to kill the well. You have to apply your underbalance until you are being sure that your debris is clean. If you are applying a static underbalance, your debris has to be taken out from your perforation tunnel. Okay, you have to be sure about that. Otherwise, you will see some productivity change, where you will say, why I got this productivity index result, it's very low. Did I make something wrong? You check it, you see the same thing again. Okay, so it will be harmful and unsuccessful operation. It can reach you to repeat the perforation in the same depth, and it's very harmful as well. Okay, so let's see some examples in here. What's the best perforation in here, for example, right? Let me there are 4 different cases. This is from SPE 71642. Okay, let me give some introduction regarding on this CFE and KC over K values. Actually, in an effort to provide the more meaningful data, the API procedure was revised in 1971. Okay, before that, before 1971, they were using well-flowing index WFI. Okay, for descriptions of this, but in 1971 they changed it to CFE, core flow efficiency value. Okay, core flow efficiency value. All right. So it's kind of indicator of laboratory performance in the linear target. Okay, we can say it's physically the ratio of flow from an actual perforation to flow from an ideal perforation of the same diameter and depth in the same target. Okay, so you have your ideal perforation value, which has been taken experimentally, and your actual perforation value. Okay, and the ratio of these two. For example, here, if CFE we say 0.7, compared with the ideal one, you can get the efficiency 70%. Okay, of the ideal one. Physically, this one. Yeah, this is the description. What about Kc over K? Kc over K also means that the crash zone and formation permeability. The formation permeability, the ratio of crash zone permeability and formation permeability. Crash zone permeability is affected what? Debris. Affected by debris directly. Debris has to be taken out. If you are reaching to 1, so you make a very good job. It means that how you are close to 1, you made a good job compared with the 0.3, 0.5, 0.7, whatever. Okay. So here, for example, 0.3 and CFE value 0.7. Test 2. What about other test results? Let me check it. Let me show all of them. Sorry. Okay, in the test 1, the CFE value is 0.7. Test 2, 0.96, very close. Test 3, 0.61, a little bit lower compared with first two. And test 4 is very low, 0.21. So what it was? Actual perforation compared with the ideal perforation. Okay. So when I come to the permeability ratios, 0.3, 0.3, 0.23, 0.04. Okay. Good. Now let me check the pressure results. Okay. Your perforation happened. Okay. This is your perforation. It shows that and then you have a lower action. You got it? You are this is you are in underbalanced condition. So what happens if you have a good connection? What you are expecting, you expect your pressure value has to be lower, like around 1000. Okay, so when you get this in test 1, I get this a little bit, but then later on something happened, but and I cannot reach. Maybe something happened in here, an extra debris created later on or something like that. It cannot reach up to these values, but in the beginning it reached that one. Okay, it reached the underbalanced condition. In the second one, this is very good. Okay, it's very good. It filled the reservoir. I have a connection with my reservoir. I can feel that. Okay, in the test 3, compared with the other two, okay, it's feeling the underbalance. It's feeling the underbalance a little bit, but still, we can say in the mid-range we succeeded. Okay, so the pressure difference gives you an idea regarding the success rate of your reservoir. So what's important? To record your pressure values during the perforation is very crucial. The best way to use it, the best way to do that is using TCP actually, okay, to become it perforation. Okay. So another examples. So here we have overbalance. What was overbalance? Your when you compare with your wellbore and your reservoir, your wellbore pressure is 500 psi higher than your reservoir pressure. Okay, you are in overbalance condition. So herein your CFE value 0.92, 0.24 in this test 8, 0.41 in test 9. When I compared the ratios of permeability, 0.79, 0.09, and 0.19. Okay. So how it happens? It seems that according to the result, it seems that test 7 has the highest connectivity with my reservoir, right? And the second test 9 test 2B, and the lowest one test 8, right? So see how it happened. Yeah, test 7 realized it very much. Okay, test 8 also realized it, and test 9 is the latest one. When I check this one, okay, here in well, how I can do that? This test 7 gives me the best result. The test 8 feeling that, but not again, something happened in after that actually, because it shows the CFE value, it shows a little bit lower compared with the other one. Okay, and in the test 9, 0.45 and 0.19, I am getting, I am not feeling a connection with my reservoir. Okay, so these are some examples that I can give regarding on the overbalance and underbalance conditions. So there is another thing. Actually, this is dynamic underbalance condition. This dynamic underbalance perforation is a kind of completion technique which uses a perforating system engineered to create a rapid underbalance immediately. Okay, underbalance immediately upon formation perforation. Okay, within what can I say? Within tens of milliseconds or faster than that. So this technique, if this technique properly applied, it improves the well deliverability by affecting cleaning the newly created perforation tunnels, cleaning your debris. Okay, so it's doing this one regardless of initial static pressure conditions. It's overbalance, underbalance, or balance, doesn't matter, because when you are doing your perforation, you are directly in underbalance condition. Okay, so in the total condition of your well doesn't matter. Okay, so although it's increasing the permeability of the crash zone that may surround the tunnel, it indeed improved the productivity of real wells. The additional process of enlarging tunnel diameter and reducing crash zone thickness further improves the productivity compared with the other two scenarios that I mentioned before. Okay, so how it makes this? Here some examples as well. For example, there is no dynamic underbalance here, and you are producing gas. Okay, you are producing gas. There is no dynamic underbalance. So see, there is a line in here. Debris still in there. You can see clearly see the debris part, especially in the last part. Okay, debris still in there. But you applied dynamic underbalance gas. Okay, this is concrete, by the way. It's concrete, I think. No, it's not concrete. This is carbonate maybe. So dynamic underbalance gas. You see how debris cleaned. All the debris has been taken. You can get it. So you have a very good connection with your reservoir compared with the first one. For the liquid, you are producing liquid. There is no dynamic underbalance. See the debris. And there is dynamic underbalance. See debris all cleaned. Okay. So the achievement of these dynamic underbalance perforating, actually it's using pure in here. So because Schlumberger has a very special product called pure, which applies this dynamic underbalance. So that's why you see pure. If you see pure, it means that dynamic underbalance. Okay, you understand it's dynamic underbalance. So it uses a special carrier guns. Okay, requires liquid around the guns. Okay. Volume, explosive load, completion, and wellbore pressure are manipulated to create the right conditions for pure perforating. Yes, you are doing this by making your calculations and model. We mentioned that. So proprietary software used for the designs, the software that I mentioned, the same software using. Okay. So according to the strength and according to the situation, you will selecting where you will load your pure guns. These two, for example, as you can see, the black ones are pure guns, which creates this dynamic underbalance. You create this dynamic underbalance by using another gas, actually. Okay. So you are using your gas in here. Maybe you will use, according to the situation, you will use 3, 4, whatever. Okay. Your design will tell you what type of gas and where you need to use it. Okay. So let's check some real examples. These are real camera examples. Okay, has been taken from in situ. So, for example, in the first part, you can see how sand debris in the crash zone. Okay, it's debris and very limited. So, a little bit actually clean, but still there are some debris. You can see. All right. So. This damage zone, you exit your damage zone. In all of them, you exit your damage zone part and you make some connections with your reservoir. But here, with your undamaged part of your reservoir, what is the connection? As you can see, just this section. So if you will get something, you will get something just from this part. Very low flow efficiency, it will be resulted. Here, you didn't connect it yet. Okay, sorry. Herein, you didn't connect it yet. Herein, you have very low connection. But if you make your dynamic underbalance condition, if you apply it well, you can get something like this, and your penetration area will be higher with your undamaged part of your reservoir, like this, as you can see in the picture, and like this, as you can see in the experiment. You will get a clean perforation tunnel, and your productivity index will be higher compared with other two. Okay, so okay, herein let's see how it happens, how this pure method, pure technique, how it happens. Let's make some analysis on that. Okay, first of all, this will be a time scale. Okay, part by part. I have a pure charge here. I have my shared charge. This making, as I said, dynamic underbalance condition applies. These are the normal detonators. Okay. Okay. So first, gun positioned on depth. We said. Okay. So your vision reservoir, your casing, your cement in here, your casing here, your cement here, your damage zone here, your vision reservoir is here. Okay. So you have your reservoir pressure, your pressure, you can see the same. So is there any dynamic underbalance condition? Yes, your reservoir pressure higher than your well pressure and your gun pressure. Okay, your well pressure is higher than your gun pressure. First condition, initial condition. Okay, let's pass to second condition. Okay, fire guns, the guns fired. The time, just the guns fired. What about the dynamic underbalance condition? There is no dynamic underbalance. Your reservoir pressure is higher than your well pressure, but your gun pressure is not higher than your well pressure. So dynamic underbalance condition is not created here. Okay. So what is need to do? Okay, there is a need to make something with this pure material, right? Pure charge. Okay, so in the third section, gun pressure released, and it reached to your casing. Okay, so what happened? Your well pressure increased a lot. Okay, your well pressure increased a lot. Your reservoir pressure is still same. Okay, is there a dynamic underbalance condition? No, your gun pressure is still high compared with your well conditions. So there is no dynamic underbalance, and of course it increased your well pressure as well compared with your reservoir pressure. So your reservoir pressure became the lowest one currently. So there is no dynamic underbalance still. I reached to cement, right? I reached to cement, casing and cement. I'm continuing for creation of the perforation tunnel. You reach your reservoir, your damage zone, past your damage zone, you reach your virgin reservoir part. Okay, so it created your perforation tunnel. it reached to maximum this is the time. It's 30 to 250 microseconds. It happens. This is the time just your perforation tunnel created. Okay. Still, I don't have the dynamic underbalance condition. So what happens? By using these pure, okay, so what happens? What's here? There is a part which has loose sand and reduced permeability part, okay, damage zone parts. So I have to get rid of this, okay. Wellbore fluid rushes in gun. There is no still dynamic condition. Now, what happened? My charts of pure charts, my pure charts start to work and start to balance. Okay, just my perforation tunnel opened, pure charts start to balance my well, reservoir, and gun conditions as dynamic underbalance condition. Okay, what's dynamic underbalance condition? Your reservoir pressure is the highest, your well pressure is the second one, and your gun pressure is the lowest one. It has to be. Okay, so what happens? Dynamic underbalance condition assured by using pure, and according to this, it starts to suck your debris and all sand part and debris through to your wellbore, right? Okay, so what happens? Your differential pressure also goes under your reservoir pressure part to apply the dynamic underbalance condition. Okay. So what happens in the seventh? Transport of failed material, all sucked by pure underbalance materials, and then you achieve a clean debris. And what happens when your clean debris, you reach your clean debris, your flow period, because you get your connection with your reservoir, your flow period starts. So you can see here your flow starting and your pressure going to balancing with your reservoir pressure. Okay, and after a while, what will happen? It will be in coherence with your reservoir pressure, and you start to flow with high productivity index. Okay. Okay, this was one of the visualizations of dynamic underbalance conditions. Okay, so another thing, this is actually a method that has been done by us. We applied first time in Iraq, this one, and it's developed by one of our perforation worldwide perforation leaders. This one, what it makes? It's your condition is overbalance condition. Okay, you don't have underbalance in here. Your condition is overbalance condition, means that your wellbore pressure higher compared with your reservoir pressure. Okay, the same things happens. Your perforation tunnel created, but at this time, what's happening in my wellbore as a fluid? I am using acid, hydrochloric acid. Okay. Hydrochloric acid I am using, and then the acid starts to penetrate through to your tunnel directly. Okay, starts to penetrate directly through to your tunnel, so your pressure starts to increase. Okay, pressure starts to increase and reach your debris material, your weak sand part and debris material. It reaches. And what happens? It reacts with the acid and directly cleaned. Okay, directly cleaned. So after that, what happens? It creates. You are in overbalance condition, right? So your wellbore pressure is still high compared to the reservoir. So what happens? It directly creates another fractures, little tiny fractures from your perforation tunnel through to the environment, closed environment. Okay. Little fractures it creates. When it starts to create fractures, little fractures, of course the pressure starts to decrease. Okay, the pressure that you are reading starts to decrease because the acid material is going through to your reservoir, and it decreases the pressure of your wellbore. But still your wellbore pressure is high, right? As you can see, compared to the reservoir. So it creates some more tinier structures, tinier fractures compared with these tiny fractures, some more tinier fracture it creates. Okay, so I got very good penetration. I got very good penetration with my reservoir in them, right? So my it continues until my reservoir pressure, until I reach my reservoir pressure. Okay, when I reach to my reservoir pressure, I can stop the operation because it means that I am in a good condition, good connection. So there may be some fractures, some natural fractures in it. Okay, in these parts, when you are making a just normal, typical perforation, maybe you will not reach any of these natural fractures, but with this type, you will reach other fractures too. So if, for example, with your perforation tool, you are not reaching, you could not connect with any natural fractures, but here you connected to 3 fractures, as you can see, right? With very high permeability, for example. So because of that, it directly increases your productivity. Okay. We applied this one for one of the client wells in Iraq in 2013, and very successful results we got compared with the neighbor well results in the same depth. We got very successful results, and we got an award of Middle East with this one. It was a very good application actually. It was the 3rd time in the world in that time. Okay, so in the end, what happens? Acid penetrates in perforation tunnel, cleans the debris part, then penetrates to formation by increasing the matrix as well as fracture permeability. Okay, so what happens? Then you can balance your condition, you start your production, and these parts are opened, all these parts are opened, you know, and suitable to production. Your oil, gas, whatever comes from natural fractures directly follows these tiny fractures that I created, and then continues its way to the wellbore, to the upper parts. Okay? So be higher and higher compared with the conventional. So another thing that we need to care about, actually, the amount of this wellbore pressure. The amount of this wellbore pressure, and this wellbore pressure has to be between the limiteds, okay, between the limits, because if you create something that your wellbore materials could not, wellbore material strength could not be enough, okay, so you can get some buckling issues, some breakage issues, and you have, in the end, maybe you have to close your well, abandon your well. Okay, so for not to reaching this one, you have to make your models, perforation models, without reaching the limitations, pressure in terms of pressure and vibrational. Okay, vibration also another thing. So you have to make your model in a very efficient way, actually. Okay, so here you can see the pressure change when your detonators explode. Okay, see top of your gun stick, bottom of your gun stick. It starts from here, as you can see now. It will repeat itself. It will started here, and it continues as a wave. It continues to the lower part and the upper parts. This pressure, see, upper parts start to feel the pressure. If it reaches something which is more than the strength of your material, okay, so it will collapse. It will have some breakage effect. It can. Okay, this is possible. So you have to know the properties of your tubing, wellbore. Maybe they used some other materials. Okay, so your well sketch is very important in here, and each part has to be put differently. Each part has to be put to your model. Okay. Okay. See, this says. Okay, this is, for example, this is the model and the actual what happened. This the herein. The red one shows your model. Okay, that has been done prior to making this operation. And the operation result is the blue one. As you can see how successful it can give the results, right? So modeling prior to make your operation is very crucial in terms of perforation and in terms of your well stabilization actually, okay? So this is another thing that I can mention. Okay, herein, so we mentioned, let me open the slides. Okay, so we mentioned case in here. The case before cleaning the perforations, before cleaning the debris and after cleaning the debris. Okay, before cleaning the debris, it's producing, you know, the percentage of water, oil, and gas production in here. Okay, blue is water production, green is oil production, and red is gas production. Okay, this is the zone, treated zone part. Okay, you can see the percentage in here. So this after cleaning the debris, see how much oil it's the oil cut increased. You can see there's no water coming anymore, and the oil cut is increased compared with the previous one. Okay, there is there is no gas anymore, not water. Sorry, there is no gas anymore, but you are producing higher and higher oil compared with the previous case. Okay. All right. So here, for example, the oil production prior to cleaning the debris, it's 770. After cleaning it, 2,295 barrel oil per day. Okay. So gas production and water production. This is gas production. Actually, color is different, but gas production. 550 to 1,050 it shows. And water cut before it was 82% and after it was 60%. I think this is not gas, by the way. This is not gas. I need to check this one. There's something in here. This is not gas, by the way. Okay, it's because there is no gas I am seeing when I compare the first two. This may be valve fluids, maybe acidizing. I will check this one. What's that? Okay. So, you can see clearly here what type of results you can get if you couldn't make your model well for your perforations, and this is a failure. Okay, this is a big failure actually. For example, it's buckling tubing. You can see what kind of buckling happens. Another buckling tubing. Okay, these are actually lucky operations because if you are facing with just buckling, so you are a little bit lucky. Of course, it will have some problems. What type of problems? You have buckling in here. It will, for example, if you want to pull inside the device near of that, you cannot do that. Okay, this type of problems you can get. But if you have a breakage, then the problems that you will face will be higher and higher compared to this one. So carefully, and it will increase the costs as well. Costs very much. So carefully, you have to do your design. Okay, this is the new tool. As you can see, this is the result of a failed tool. See what type of difference it shows. Wrong perforation, wrong calculated perforation result. Okay. All right. So these are another example. This is another examples for valve bore dynamics. Okay. So if you stays inside the limits, there will not be any problem. If you have here they used, okay, if you put just one tubing size in here, so you can make miscalculation here as well. So for the differential pressure calculations, you have to put your well sketch in right places, in right depths. Each of them has to be calculated separately. Okay. All right. So this is all my presentation. If you have any questions, I'll be glad to answer your questions. Yes.
Hi. Can you hear me?
Yes, I can hear you.
Yes, yes.
I have not a question, but I want to say, can you please share this presentations with us? All of this, all 4 weeks
Okay,
presentation.
I will try to make a PDF version of this one because it includes some materials inside, okay, which I had done actually when I was with Schlumberger. So I will try to share it by taking out some parts of it, of course. I will try to do that as PDF versions. I will do that.
All of them?
Okay. Not all of them. I cannot share all of them. Some parts I need to take out because it includes some Schlumberger material in it.
Yes, yes. I don't mean it. I mean it before previous weeks presentations.
Sure. I will share all 4. No worries about that. But with taking out some slice of that, okay? I will share for all 4. No worries. Okay.
Thanks. Good night.
Thanks.
Okay.
Can you mention pressure generators? I think there is a question in here. Let me firstly describe that. Later on, I will turn back. Can you mention pressure generated during perforation job in field? Okay. In the end, this is an explosion. Okay, this is an explosion. This is a kind of chemical reaction which creates extra pressures. Okay. So when you explode something, for example, a TNT or whatever in the surface, right? You see what type of pressure you can get, right? It creates incredible amount of pressure around. You can feel that one. According to the explosive and the explosive, of course, it changed, but it creates, each explosion creates pressure, definitely, temperature and pressure, okay? So herein, of course, it will create the extra pressure and temperature, and it will affect your wellbore condition, even your reservoir condition as well, okay? So why your debris material is created, we mentioned in here, because of the extra pressure that the guns produced. Okay, so because of that, you have to adjust your pressure limits. You have to know your pressure limits and adjust the amount of the explosive that will use and the places of your explosive that will use in wellbore exactly. Okay, exactly. This needs to be described. So because of that, it is very important to make a model for your pressure that will go in out when you explode these devices. Okay, this is the role of pressure that I can say. All right. Okay, so one more questions I heard. Actually, is there another question? No. Okay.
I have a question. How much
Please.
time we use this perforating process in just one well, or
How many
this
times?
procedure?
How many times? You mean how many times? How many times we use perforation in one well?
Yes.
Okay, so herein, let me describe in one you can use multiple perforations. So you reach that depth, there will not be anything more, or we will continue later on. Okay, so you reach your the results of your drilling, the results of your actually testing, wireline testing, maybe some PLT results, whatever, you know in which depth intervals you have productivity. Okay, you have oil productivity, gas productivity, or you have more water cut. Okay, for example, in one well, if you have 3 different proactive zones in certain depths, for example, one of them is 1,200 meters, other one 1,400 meters, the other one is 1,500 meters around. Okay, I'm saying that 1,480 to 1,520. Okay, 40 meters active zone you have. So you can arrange different perforations for all different zones in 3 different types, or you can manage it in once as well. Okay, this is possible as well. In once you can manage it, or in 3 times. For example, if you are using a DST string, you have to manage it in 3 times. Okay, you will put it to the lowest part. Okay, for example, we said 1,550. You will put your interval, and the lower part of your interval you will put your packer. Okay, you will isolate the interval, and you will explode your guns. You will start productivity, and then you will pass to upper part, and then with new guns you will start, you will isolate the and the third one you will try the same thing. 3 times you can try this. Let's talk about a scenario. For example, the lowest part or the middle part, middle interval, could not be successful because of the modeling and other things. You could not make it very good. Okay, so you could not clean your debris part, and your productivity is lower. One of them. Okay, let's say lower part, the lowest part. So in this case, what you will do? So maybe you can choose to use DST string again to go to the lower part after these 3 perforations. To go to the lowest part, you can select, or you can use some wireline devices, whatever, but you have to isolate your zone again. So your interval need to be isolated again, and you have to maintain your conditions according to these underbalance or overbalance, but it depends on your design. Okay, so you can reperforate it. There is no problem, but the problem is in here. For example, you perforated it with 60 degrees. Okay, you have some production, but you will reperforate it, so you have to analyze it well again. Okay, you have to consider that it's it has a primary perforation. Okay, you have to put it to your model as well. Okay, with not cleaned debris. Okay, you have to put it, and then reperforation is possible, no problem. But of course, costly. It will be costly if your production compared with these last section in upper 2 sections, for example, is you are having a commingled flow. For example, if your production with the first 2 zones is good, so you cannot think about that in close time. Okay, but in long time period, maybe it will be beneficial to go, for example, after 3 years, 4 years, the production of the first 2 intervals start to make some water cut, high water cut. So you can decide to go to the lowest part, and you can reperforate it after 3 years, for example, 4 years. Okay, these are operations that can be done. Of course, they increase the cost, but it's possible directly. It doesn't have any problem. You can do that. No worries. Okay. All right.
It was clear.
Thanks
Thank you
from
so
my
much.
side. Thanks from my side. It was beneficial for me, for all of us. I also had a chance to repeat the things that I performed previously. So I believe that it become a very good sections for you as well. Some operational parts included, some modeling parts included, some structural parts and behaviors of fluids and rocks included. Hope that you all enjoyed that one. It was a pleasure for me. Nice to meet you all, and hope that we will meet again. All right.
I am very thankful behalf of me and behalf of my teams. We are very grateful that you have teach us such an informative and interesting session each week during the 1 month, and I'm sure that students also very thankful, and thanks again.
Thanks from my side. Thank you.
Also, firstly, nice to meet you, and all of these parts, including today's part of this 1 month workshop, was very interesting, fruitful, and informative. We learned together with you lots of knowledge related to our specialty area, and all of them would be very useful in our future career. We appreciate it by the name of SPE Khazar University, and thankful to you. Good night and have a good weekend.
Thank you very much. It was a pleasure. Thank you.
Please, before the leaving, can we take an group image?
Of course.
Teacher, can you stop the screen sharing?
All right.
Okay.
I'll stop the idea.